Good day, good day, good day, my lovely people on the internet. It's me again, Jazzy, but I'm alone again, sadly. Not funny. All right, let's stick to the maths. Today's topic is vectors, not insect vectors like mosquitoes. Anyway, you see in maths, a vector is a quantity that has both magnitude and direction. If it only has one of those things, it isn't a vector. It must have the two. Let's look at an example. Let's say you are shielding yourself from the sun by standing next to a tree. But the sun moves as the sun tends to, forcing you to move as well. Let's say you move. It is 10 meters away from where you were originally standing. Well, that 10 meters you move is a magnitude of distance. So is 10 meters a vector? No, because we did not specify which direction you moved in relation to the tree. But if we say you move 10 meters to the left of the tree, now we have added direction to the quantity. The magnitude, which is in this instance the distance, as well as the direction together makes a vector. I'll repeat that. Both the distance and the direction together form the vector. A real-life example of a vector quantity is velocity. Velocity is a quantity that shows the speed of an object as well as the direction in which the object is moving. If we say a car is moving at 3 kilometers per hour, we have just described the speed of a car. But if we say it is moving at 3 kilometers per hour, 4 degrees to the north, we have just described its velocity. And that's what a vector is. Now, vectors are used in mathematical equations, but before we get into equations, let's first cover a few things. Alright, I'll be honest, it isn't a few things. It's a little more than a few things, but remember, don't panic, it's just maths. Alright, so, vámonos, let's go. Number one of the tools people use to think about vectors are vector arrows. Vector arrows are like snakes. They have a head and a tail. The head and tail are usually given corresponding letters like A and B. The letters could be any letter, it really doesn't matter. Sometimes vector arrows are also given tiny letters to represent the entire vector arrow, like the common letter A. Number two, remember, this is not an art class, this is a maths class. So these letters are going to be used when we are writing vector expressions and equations. In an expression, you can write this vector as either AB with an arrow on top or just A. If the letter on your vector arrow were J and K with a little j in between, it could be written as JK with an arrow on top or as little j. Number three, in vector arrows, the length of the arrow represents the magnitude of the vector, and the head of the arrow indicates the direction of the vector. Number four, vectors can be represented on a graph. Here we have our Cartesian plane, as they are fancifully called. On a Cartesian plane, we have an x-axis that runs horizontally, and we have a y-axis that runs vertically. Y'all remember that, right? Let's plot this graph using our velocity vector from earlier. Let's put our speed in kilometers per hour on the x-axis and our direction in degrees on our y-axis. We can represent this velocity vector with a single line that shows both the direction and the magnitude, which in this example is the speed. That is how the vector is represented on a graph. And finally, number 5. The magnitude and direction values of a vector can also be written in expressions and equations. And for that, we use something we learned about in previous videos. A matrix. A 2x1 matrix to be exact. So let's say the vector arrow AB represented our velocity vector of 3 kilometers per hour, 4 degrees to the north. It would be written like this. AB with an arrow on top, or A, little a, is equal to a 2x1 matrix that has the value x on top and the y value below. Remember, x on top, y below, which in our example would be 3 kilometers per hour on top and 4 degrees to the north below. X, y. And that pretty much covers all you need to know about vectors. Psych. That's just the basic bare bones of vectors. We are now going to use all of these fundamental principles to do mathematical operations like subtraction, addition, and even multiplication. Let's begin with addition. Let's say we are adding a vector A to a vector B. Their vector arrows would be drawn like this. The addition of A and B together, however, would create a new vector, which we draw by joining the tail of the first vector to the head of the last vector, like so. That's how we add using vector arrows. But let's look at the actual number values of these vectors. If A is equal to a 2 by 1 matrix containing the values 8 and 13, and B is equal to a 2 by 1 matrix with the values 26 and 7, then A plus B is added just as you learn to add matrices. 8 plus 26 is equal to 34. And 13 plus 7 is equal to 20. Vector A plus vector B is therefore equal to a new vector containing the values 34 and 20 in matrix form. Simple enough, so let's scratch that and turn now to subtraction. To subtract a vector, we first need to understand what a negative vector is. A negative vector is a vector that has the same magnitude but opposite direction. For example, let's say we have a vector PQ with an arrow that points in this direction. It's equal to 8, 10. The negative of this vector could be written in 3 ways. Yes, 3 ways. It could be written as PQ with the arrow pointing in the opposite direction to the left, or it could be written as QP with the arrow pointing to the right. Note that QP with the arrow pointing to the right is the exact same as PQ with the arrow pointing to the left. Thirdly, if the vector arrow was represented by a small letter instead, such as P, then the negative of P would be written as well, negative P. We show this because when dealing with vectors, we prefer that you think of subtraction as the addition of negative vectors. Here's why. Going back to our first example where vector A was equal to 8 and 13 and vector B was equal to 26 and 7, if we were to minus B from A instead, this is how we would show it as a vector arrow. The vector B, when negative, goes in the opposite direction like so. And now we show the value of a minus B by joining the tail of the first vector to the head of the second. This operation is exactly what we did for addition. That is because it is addition of a negative vector. A minus B, therefore, will be subtracted just as we learned to subtract matrices. 8 minus 26 is equal to negative 18, and 13 minus 7 is equal to 6. A minus B is equal to a matrix containing the values negative 18 and 6. Let's look at position vectors. They start at the origin of the Cartesian plane. Example OA 3, 4 and OB 8, 1. Now let's say they ask us for vector AB. Using our knowledge from before, we can apply this golden formula. AB is equal to AO plus OB. Now AB values weren't given, so we have to find it. I like to say you're driving from A to B, but A to B was not mapped out, so we need to find another route that was mapped out. We do know OA and OB. From our formula, to get to AB, we go AO and then OB. Note we must start at A and end at B. If you look at the formula, there are some O's in the middle. The O's are in the middle. But we do not have AO, or do we? Well, AO is the negative of OA. Remember that. Therefore, AO is the negative of 3 and 4. So AO is minus 3 minus 4. We have OB, so we don't need to figure that out. So we've got it. AB equals AO, which was the negative of OA, remember that, plus OB. AB equals AO plus OB. Minus 3 minus 4 plus 8, 1. minus 3 plus 8 equals 5, minus 4 plus 1 equals minus 3. Therefore, AB equals 5 minus 3. And last but not least, for today's episode, we will look at scalar multiplication of vectors. This is when we multiply vectors by scalar or real numbers. Scalar multiplication of vectors follows the same rules of scalar multiplication of matrices. The scalar is multiplied by each number contained in the matrix. Let's say a vector y is equal to a matrix containing the values 4 and 3. Then 3y would be equal to the scalar or real number 3 multiplied by the matrix y. 3 multiplied by 4 is equal to 12, and 3 multiplied by 3 is equal to 9. When drawing this, remember when we said that the length of a vector arrow represents the magnitude of that vector? Well, now that the magnitude of this vector has been multiplied by 3, we show this by making the vector arrow 3 times longer. And that brings us to the end of our video today on vectors. Well, our first video at least. Stay tuned to OpenSec Math as we continue on the topic. And remember, don't panic. It's just maths. This video is sponsored by BP and produced by the 2 Cents Movement with the help of these beautiful people. Be sure to like, share, and subscribe to our channel for more videos. And remember, don't panic. It's just math.